Assalamualaikum, Doctor.
Waalaikumsalam. Waiting for others to enter.
All right.
There's 8 students remaining. Okay, so Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and good morning. So, referring to slide number 66. Okay. So last week I already discussed with you regarding the difference between the open loop transfer function and closed loop transfer functions. So when you're given an open loop transfer functions, okay, something like this, j omega 1 over j omega 1 plus j omega 1 plus j omega 0.5, where j omega is equal to s, where s is the Laplace operator. So we can plot both plot in open loop mode and closed loop mode. Okay, so if open loop like this, j omega, you just straightforward. Okay, go to the MATLAB and type the command to plot the open loop transfer functions. But for closed loop transfer function, of course, you have to find the closed loop from the j omega. Let's say this is the closed loop transfer function. So it will be 1 over j omega, okay, for the closed loop transfer function. And then after that, you observe the coefficients and then you can plot. So as I told you before in last week, okay, for open loop transfer functions, we can get 5 important information, okay, which is the gain margin, phase margin, gain margin frequency, and phase margin frequency, and magnitude 0 decimal, and stability status. Okay, so please remember these 5 main points. And for the closed loop transfer functions, okay, for both, you can get 3 important information, which is the peak magnitude, which is NP, peak frequency, and the bandwidth, okay, which is omega B omega, right? So come back to the examples, which is on the slide number 66, where you consider the unity feedback system with an open loop transfer functions as shown here, okay? So you are required to determine the gain margin, phase margin, omega GM, omega BM, and system stability, and the peak magnitude, the peak resonant. Okay, this is another name for peak frequency. We call it as a resonant frequency, and the bandwidth of the frequency. Right. So by using MATLAB, we can obtain these informations, 5 informations straight away. Okay. You can see that the omega GM, okay, where the phase cross minus 180, okay, which give you the gain margin of 9.54 decibels, and the omega PM, which is occurred at the magnitude 0 decibels, which give you the phase margin of 32.6 degrees, okay. And the frequency of omega GM is 1.42, and omega PM is 7.749 radian per second respectively. And because of the positive gain margin and positive phase margin, so the system is stable. Okay, so remember the positive. Okay, then the closed loop, you have to rewrite the transfer function from the open loop. Okay, you manipulate the open loop transfer functions become closed loop transfer function as shown. Okay, where by using MATLAB again, so you can plot it, where you can see that the plot is different. Okay, the plot is different for the phase and for the magnitude in decibels. Okay, so we plot it and then we obtain the peak magnitude, okay, at 5.28 decibels. So magnitude, peak magnitude can be in decibels or can be without decibels. So if you want to change to without decibels, okay, which is you have to do anti-log, okay, as shown here. 10 power of 5.28 divided by 20, which will give you 1.8365, okay, which is equivalent to 5.28 decibels, okay. The difference is one is 20 log m, the other one is without 20 log m. And then at that particular frequency is 0.824 radian per second, which is at the peak of the magnitude, and therefore for the bandwidth you have to scan, okay, each point of this. Okay, you scan using your mouse, then you will get at minus 3 dB, which is here. The frequency is 1.26 radian per second. Okay, so you must know the tips there for magnitude, for bandwidth. The magnitude of the closed loop must be at minus 3 decibels. So another examples in my notes. So I put a lot of examples for you to try and to understand the concept of frequency response in control system. So this time again, J omega, which is S, 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 and S. Okay, so in order to do the searching for this value, so you can multiply or straight away you use the command that I showed to you last week. Okay, then same thing. Okay, find the GM, find the PM, omega PM, omega GM, and system stability. MP, omega P, and omega bandwidth, but there is another challenging, which is the challenge, which is you have to find the zeta and omega n, which is the damping ratio and undamped natural frequency. So we plot it. Okay, so we obtain omega GM 4.13 radian per second, which is here. Okay, omega GM, and the phase margin, the gain margin is 7.36 radian per dB, and omega PM is over here. Okay, which is sorry. Okay, that is omega GM, and this one is omega PM. Okay, which will give you the phase margin of 18 degrees positive. Okay, stable, PM and GM positive, still stable. Then do the closed loop. Okay, rewrite the transfer functions from the open loop. Okay, just +5 at the bottom. Then you will get the peak at 10.3 decibels, which is equivalent to 3.2734, which is 10 power of 10.3 divided by 20. And the peak occurred at the 2.71 radian per second, and the bandwidth at -3 decibels here, okay, is 4.16 radian per second. So the damping ratio and undamped natural frequency can be represented by this formula, okay, which is in the slide. I can't remember, okay, the previous slide, which is 1/2 zeta 1 minus 2 zeta square. Okay, so this value is not dB. So please remember. Okay, the value 3.2734 is MP. Okay, which is not dB. So if you put this one as 10.3 dB, so you will get the wrong zeta. Okay, so please make sure that you put the right value of MP without decibels. Okay, which is here 3.2734. And then the omega P here is 2.71. Okay, so once you get the zeta, you insert here, then you will get the omega n. Okay, so can this one, if you put it down here, is 1/2 zeta multiplied by 3.2734. Okay, square root 1 minus zeta square. So 1 minus zeta square, okay, is equal to 1 divided by 3.2734. Multiplied by 2. So 6.5868 zeta square. Okay. So can somebody help me to find the zeta? This one?
0.987.
Zeta is
0.987.
7, eh? Okay. And then once you get the zeta value, then it goes to this formula, which is omega n. Okay. Omega n, which is 2.71 divided by 1 minus 2 0.987 square. Okay. Then what is the omega n value? Omega n value. Somebody please help.
X times 0.9.
Is it 0.974?
0. Point. Omega n 2.71 divide by square root 1 minus 2, 0.987 square. What is the value?
So x is zeta. What is x? 1 minus 2x, is it?
1 minus 2 zeta square.
2 zeta square. I don't know why I got a math error when I tried to multiply it.
You get math error.
Yeah, I'm gonna try it again.
Okay, you try again and then you share in the WhatsApp list, slide 72. Okay, slide 72, what is the value of zeta and omega n? Okay, okay. Maybe the zeta value is wrong, so you have to check again. Okay.
All right, got it.
So we go to the, after you get the value, you share in the WhatsApp list, slide 72. Consider the unity feedback, the next example, with an open loop transfer functions. So determine the corner or break frequency. Okay. So from here, you already know that the break and corner frequency, there is a 2, okay, BF. Okay. BF is not a best friend, but break frequency, which is 0.05 and 2.5. Eh? Then determine the open loop plot of gain margin, phase margin, and system stability. Then find NP, omega P, and omega bandwidth, and find the approximate value of zeta and omega n. See, this question is very straightforward for chapter 3. Okay, so we will be asked in the quiz in some way, some in June, inshallah, for quiz. For chapter 3. So very straightforward questions. Okay. So from the open loop boot plot, okay. So we plot it. So you can see that there is a 2 corner frequency. Okay. From this plot, which is at 0.05 and 2.5. So this plot is start from here, which is 0.001, 0. Oh, sorry, this is not 0.01. This is 0.0, 0.01, 0.1, 1.0, 10, 100, and 1000. Okay. So it happens between this region and this region. Okay. The corner frequency. So
How can you tell, doctor? How can you tell that it's between those two ranges?
So if you see this one, okay, this one is a GS 50 1 plus 0.05S, okay, plus J 2.5S, okay. So 1 over 0.05 berapa? And 1 over 2.5.
20 and
1 divided by 0.05.
20.
20. Okay, radian per second, and 2.5.
0.4.
2.4.
0.4.
Okay, so the range, oh, not here, sorry. The range is not here. The range is between here, 0.4. Okay, 0.4 here. There is one corner frequency over here, and 20 is somewhere here. Okay, so 20 is somewhere here, the corner frequency. So the corner frequency is 0.4 radian per second and 20 radian per second. So this the range of this one, decade, and this decade. Okay, you cannot see from the real plot unless you plot it in the straight line approximations, okay, or we call it as a apa nama dia, lupa dah. Straight line approximation. I forgot the names. There is a names for it. So we call it a straight line approximation, but this one is a real plot. So the question asks you what is the corner frequency. So the corner frequency is by looking at the transfer functions is 1 over 0.05, which is 4 radian per second, and 1 over 2.5, which is 20 radian per second. We can get straight away from the transfer functions. And then we plot, so we obtain the gain margin 68 decibels and phase margin 53.3 degrees. Both are positive. Okay, both are positive and it is stable with the omega GM and omega BM as shown. Then for the closed loop, we just add 50 at the denominator and then we find the 1.01 decibels. Then we have to convert this value into the 1.1233 because we're going to use this formula for the zeta value. Okay, and then omega P, we will get omega N value. Okay, and then omega bandwidth is 25.2 radian per second at minus 3 decibel. And again, by using this formula again, okay, so you will get 0.513 for the damping ratio and use this value inside the zeta square, then you will get omega N at 22 radian per second, where omega N is equal to omega P divided by 1 minus 2 zeta square, 14.8, 1 minus 2, 0.513 square. Another examples, I think this one is similar as well. So you have to find the corner frequency. So from here, we already acknowledge that we have the first one, FB1, which is 1 over 0.2. Berapa?
5
radian per second. And the second corner frequency, which is 1 over 0.02.
50.
50 radian per second. Okay. So S is the integrator. So this make the system is type 1. Okay, because of the poles at the origin. So we plot, okay, so the value is there, okay. Gain margin, positive 14.8 decibels. Phase margin, positive 31.7 degrees with omega GM, 15.8 radian per second, and omega PM, 6.22 radian per second. Then we obtain the closed loop transfer functions. Okay, so you get MP is 5.28 dB. Okay, so the peak will be at 5.28 divided by 20. How much for the peak? This one is 20 log. 10 power of 5.28 divided by 20?
1.836.
1.836. Okay. Okay, so we're going to use this formula to obtain the zeta value. Okay. And then the omega bandwidth at minus 3 decibels is 10.2 radian per second. Okay. So zeta and omega n is here. So I left it here. So please help me and share your answer with us. Okay. Slide tadi slide 60 apa? Slide 80 and
72.
slide 80 and 72. Okay. Kindly share your values according to the slide number. Okay. So for omega bandwidth, you also can use this formula. Please don't memorize this formula. Formula is given. Okay. In order to find all the other specifications, okay, of the frequency domain and time domain values. So at the end, we find the relationship between the closed loop time and closed loop frequency response. Okay, so closed loop time to give you the time response, closed loop frequency response is to give you the whole response of the frequency for that particular system, where the omega bandwidth, omega BW, and the time response spec is shown here. Okay, omega BWTS versus zeta graph. Okay, so this is the damping ratio. And this one is the omega bandwidth multiplied by TS. So this one is considered as the standard curve. Okay, standard curve. And what is the equation for this? Equation for it? What is the equation for the this equation, this curve? Equation is here. This is the equations.
Second one.
The second one. Okay. Okay. So this one refer to number 2 equation. Okay. So the equation is very complicated. Omega BW. So TS you bring up, multiply with omega BW so that you get omega BW multiplied by TS. And then this is zeta. So zeta left over on the right hand side of the equations, which is a square root over square root. Okay. Is the power of 4. So this curve, either this curve or this equation number 2 will be given. Okay, either one, or sometimes it gives both. Then for the omega bandwidth and the time response specification is omega bandwidth TP. Okay, versus zeta. So it's on the y-axis, omega bandwidth TP, multiplied with the damping ratio on the x-axis, and it will give you this standard curve. And this curve is represented by equation number here, number 3. Okay. Okay. So refer to equation number 3 for the formulas of this curve. Lastly is the omega bandwidth time versus time response. Okay, this curve. Okay, omega bandwidth TR. Okay, is the rising time versus the damping ratio zeta. Okay, so this one is represented by equation number 1.
Where did it TR?
No TR, so TR is not given here. Okay. The formula may be in the normalized book. Okay, it's listed there. Okay. So equation might be in Norman Nice book chapter. I already WhatsApp to you the what do you call that? The book chapter, okay, which is here. Okay.
Which chapter could it be?
Yeah.
Locus, no.
Okay. Pen, comment. Okay. Okay. So this book chapter will explain what I lectured last week and this week. So I'm trying to find the omega bandwidth TR. Is it available here? Okay. Okay, this one is okay. So it's more details here compared to my slides. Okay, so you should read it. Okay. Quiz. Okay, no quiz. No quiz. Okay. For our class, quiz can be ignored. Nichols chart also can be ignored. Okay, not included in the exams and tests. Okay.
The closest I can get is page 48,
Page 48.
but it gives the same formula that the slides gave. There's no TR.
Page 48 is here. Okay.
Yeah.
Okay, omega BW, omega N. So there is no TR. TR is not given. Okay. We give equation number 1, which is omega BW and omega N. And then equation number 2 and equation number 3. Okay. So equation number for TR is not available. Okay. Never mind, just an options. Okay. For the student to try. Okay. So we go back to here. So far, any questions? Any questions from the class?
I have a question, Doctor, regarding the corner frequency.
Yep.
If we already get the exact value of corner frequency, why do we have to like put a range in the decade?
Just mentioned the range is because the location of that corner frequency in between the minimum and maximums. Okay, nothing to do with the value of the corner frequency. If you don't want to refer to the, if you refer to the real actual plot, it's difficult to find the corner frequency because it's already sum up all the factors. Okay, gain factor, poles, zeros, all are sum up. So very difficult to observe corner frequency from the real plot given. So the best way is get from the transfer functions, and then you can get the values of the
range
corner frequency straight away. No need to mention the range. Okay, no need to the range.
Okay, thank you.
So this one is the relationship between the closed loop time and closed loop frequency response. So find the closed loop bandwidth required for 20% overshoot. Okay. Slide number
80 something. 84.
Okay. For 20% overshoot. And the settling time 2 seconds. So use the damping ratio formula, which is here. So this formula is very common and popular, will be given in the test and in the exams. Okay. So you get straight away 0.456 for the damping ratio, which correspond to 20% overshoot. Okay. So by using the settling time 2 seconds, okay. So you can use the value of the TS and the zeta, okay. So you will get the bandwidth at 5.79 radian per second, just a straight away plug-in formula based on the given and calculation value. So example 5. So this one is, we will look into the boat plot manipulations where we adjust the gain, okay. So for example, for k equal to 1, that is the initial gain, then we want to change to k equal to 10 by pulling, also by rotating the knob of the potentiometer or the variable resistor. We want to increase the gain and see what happened, okay, to the frequency response. So you are given a unity feedback, which is the k over s, s plus 1, s plus 2. Okay, so using a MATLAB, find the system gain, the phase margin, okay, the maximum amplitude, and the bandwidth for k is equal to 1 and k is equal to 10. Okay, so you can obtain the gain margin and phase margin from the open loop transfer function, and for the maximum amplitude and the bandwidth can be obtained from the closed loop transfer function. Okay, so if you look here, okay, this table is given by the comparisons, okay, between k equal to 1 and k equal to 10. So what is k? K is the gain, okay, the gain value of the transfer functions, okay, which is here, k. So when we plot, we obtain the gain margin 29.5 decibel for k equal to 1 and 9.5 decibel when k equal to 10. So phase margin is 78 degree positive, both are positive, both are stable. And the maximum amplitude for k equal to 1 is 0 decibel, for k is equal to 10 is 7.3 decibel, and the bandwidth is 0.26 radian per second and 2 radian per second, which is for manually calculations, okay, is very difficult, but you can scan throughout the computer, okay, by using the graph that we plot. So this is k equal to 1, the plot for the frequency response, open loop transfer functions, okay. So guys, you can see that the gain margin is positive, the phase margin is positive with the frequency at 1.41 and 2.09 respectively, and the system is stable. So from the plot, we obtain a positive gain margin, okay, and positive phase margin, okay, and the system is stable, right? Then closed loop, okay, we just add k, okay, at the denominator of the transfer function closed loop. Then you can see that the peak gain is about 0.921 decibels, okay, but in the table is 0 1. Actually, this one 0.921 decibels, okay, from the computer. And the peak frequency is 0.454, and the bandwidth is at 0.793 minus 3 decibel per decade, minus 3 decibel magnitude. So this is the information that we can extract out, 0.921 decibels, okay, 0.454, the peak frequency and the bandwidth, okay. Then we change to the open loop, okay. So we change to the open loop boat plot, okay. So we can see that at the gain margin becomes negative, okay. The gain margin becomes negative and the phase margin becomes negative. while we change from the gain from k equal to 1 to k equal to 10. So the system is not stable anymore. Okay, it's not stable anymore. We give a gain margin of negative and phase margin of negative at 1.41 and 1.8 radian per second, unstable. Then we change to the open loop transfer function by adding k at the denominator with k is equal to 10. Then you get peak gain is 14 at 1.72 radian per second. And the magnitude, the bandwidth is at 2.52 radian per second at -3 decibels. Okay, you can see the plot is different when the phase, especially the phase, when we apply the closed loop transfer functions. So this is the data with 14 decibel, 1.72 radian per second, and 2.52 radian per second. So we already try k is equal to 10, k is equal to 1. Okay, so this one will give you stable, this one will give you unstable. So try k equal to 6 and see what happened. Okay, so this is another way to plot the Bode plot by multiplying all the polynomials. So you can see that this one is 1, this one is 3, this one is 2, and this one is 0. So that's why I key in as denominator D 1320, and the numerator is 6, which is a single numerator at 6 value, and then both N, D, numerator and denominator. You can see that here. So what is your observations, Azira Ahmad? When we change from k equal to 1 to 10, then we change to k equal to 6. Azira,
Yes.
what's your observations from the...
The gain margin was very small.
Small tu berapa?
Power of negative 15, so 0.000 0 dB, yes.
Phase margin
It was also 0 dB.
0 dB, astaghfirullah.
No, 0.0
degree.
degree phase, sorry.
Omega GN,
Omega GN is 1.41 radian per second.
and omega PM.
Omega PM 1.41 radian per second.
So the stability status.
Stable because it's positive.
Stable is wrong.
Yes.
Critical
Marginal.
Marginal.
Marginal stable.
Marginal. I see. Okay. Marginal for critical. Ingat tak? Azira.
Okay.
Okay, bye.
So that means kalau dia sama, dia marginal ke doktor?
When I told you already, omega GM equal to omega PM once it is equal value. Okay, let's say for this case, which is 1.41 radian per second. So it is marginal or critical.
Oh.
Okay.
So it doesn't have to be 0? Could be any value as long as it's similar.
What is 0? 0 radian per second.
Yeah. Frequency.
The gain margin is 0.
Gain.
The phase margin is 0 degrees.
Yeah. Okay, got it. Sorry.
Okay. We have 3 cases only. One, k equal to 1 is stable. K equal to 10 is unstable. So when we rotate the knob of the pot meter, k equal to 6, so it become marginal or critical. Only 3 conditions. Just remember 3. There is no 4, 5, and so on. Okay.
Okay, that's it.
So it is an analysis from the observation, 0 decibels, 1.41, 0 degrees, same, marginal stable. Okay. Due to the 0 value of gain margin and phase margin. And the gain crossover frequency, omega GM, and phase crossover frequency is the same. So we see the plot. Okay, you can see that there is a sharp here. Okay, very sharp, like an impulse. Okay, what is the value of that frequency? Low Zhaotian?
150.
Kan omega p what is the peak frequency over there?
So shouldn't the peak frequency be equal to the previous
No,
of 1.41?
no, this is k equal to 6.
Wouldn't it be equal to the previous one with 1.41 as well?
Oh, this one is a closed loop. Example. Closed loop.
Oh,
This
okay.
is close.
This one is open loop, telper. Closed loop is different. Okay, so Paul Zheng Han, what is the omega p value?
Omega P. Not sure. I think.
Ini satu, this is 1, this is 2.
Oh, okay. So it's like about 1.41, halfway between 1 and 2.
1.5 radians per second.
Oh,
You
1.5.
know how to read a data, no, a graph. You will graduate in 1 year time. When the technician show you this graph, frequency response, they don't know. So you have to guide them.
Okay, sorry.
150 decibel, you don't give just read it, okay? All in there, okay? The data can get in numbers. You can get data in numbers, crunching numbers, a lot of numbers, data. Or we can get in the graphical, okay? A graphical without data. So if you give a graphical, so you must know how to read, okay? You must know how to read. Okay, we have a analysis. Okay, this is analysis. Okay, I already discussed it then, 1.41. Dalam slide, ada dalam slide. And the bandwidth is 2.09. And the system is critical. Okay, we have a break, 10 minutes. Okay, guys, 10 minutes.
Okay.
Okay, doctor.
Acknowledge.
Okay, guys, we continue. $25 attendance, 24 attendance. Okay. Can we start?
Yes,
Yes,
doctor.
doctor.
Right. So I want to share you this figure. Okay. You're given a plot. Okay. Can you see?
Wow, that's a lot of noise.
Can you see the plot?
Yes.
Telpel,
Yes.
can you give your comment on this? As an engineer, future graduate engineer.
It fluctuates a lot and can show the complete incompetency of our government. It constantly.
What?
First, as an engineer, future graduate engineer, you have to tell
As an engineer,
your staff below what
can
is
have,
the graph of this. It's the graph of what?
you see a steep increase from the initial months, but then a slow decrease, then another exponential increase back again.
So to make it simple, short and sweet, can we ask another student, more wages?
Yes, doctor.
As an engineer, future graduate engineer, just graduate, first salary 5,000 per month. So what you should tell this information that you receive, okay, from the KKM to your staff under your supervisions.
The case will increase more.
Increase, decrease, increase. First, you have to tell them this is a graph over new cases of COVID-19 versus time frame. Am I right?
Yes.
Months. Am I right?
Yes.
Okay. Hello, guys, are you sleeping?
No.
No,
Listening.
Yes,
no. I
doctor.
thought you were asking Lojin on loan. Sorry.
Hidup.
So you as an engineer, but under you there is a lot of technicians, there is a lot of technical assistants. So you're going to take some precautions, strictly SOP. So as an introduction, you give this graph to them. Okay, so this graph have two lines. Can you see two lines? One is the solid lavender, purple. We call it purple.
Purple, yes.
Okay, solid line, which is real data from KKM, daily new cases. That is the real data reported by the KKM. What is KKM? Is the Ministry of Health. Then we have another line, which is the blue dotted line. Blue dotted line is the line of prediction of new cases. Prediction is not sometimes correct, sometimes not correct, because it's based on the mathematical model. Okay, mathematical model that we learn in chapter in control 1. Okay, so we compare simultaneously in one graph. Okay, so we can see that the trend, okay, the daily new cases trend is follow the
Prediction.
model. Okay, so you can see that in month of January, we have a peak because of the SOP is not follow strict in a strict manner. It happened peak at the February and early February. Then it goes down. Okay. Then suddenly school open. Right. School open in early April, end of March. Right. And then the case start to rising. Okay. Start to rising again until this one. which is they predict in 1 week time, in next week lah, that will be the peak lah, where we celebrate Eid Mubarak or Hari Raya, okay? And then the case will go down, okay? But if they allow cross-state, okay, so this prediction model is not valid anymore, okay, because there will be another wave, okay. So we already have a first wave here, okay. This is your first wave, okay. Somewhere here, first wave. Then this is your second wave, and this one is definitely a third wave, okay. Okay, so it's come and go because first is because of the not following the SOP. Okay. Second is a very slow vaccination process. Okay, and other factors that contribute. Okay. So can you understand how to explain this, Nur Aina Shafika?
Yes, doctor.
You are appointed as an engineer, newly graduate engineer. Okay, you have 50 staff under you. Can you explain this data?
This data is about COVID-19. Lepas tu, before Hari Raya Aidilfitri, estimated dia kalau
In English, we have Arab brothers here.
okay, before Aidilfitri, if we not obey to the MKN rules, the expedition will not be verified anymore because MKN not allowed us to go through other states before Aidilfitri and after Aidilfitri. So
Okay lah. Can be engineer lah, 12,000 per month lah, starting salary. Okay, Delpel. Okay,
Okay, doctor.
simple. You have to explain people very simple things in a very easy manner, so that people can understand. Okay, so don't make things complicated, fluctuate. They don't understand the word fluctuate. Okay, so you can see that the real data and the prediction model. How smooth is it? Of course, the mathematical model is smooth. Am I right?
Yeah.
Because there is no disturbance, there is no uncertainties, there is no noise. But if you really measure the data, you can see that there is a fluctuate. Okay.
Especially the peak.
Yes, that fluctuate meaning that is the real data, the real life, the reality, okay, of the real data measurement. That is what I'm going to explain to you. So similarly, same to the here. Okay, come back to the frequency response. As I told you before, the relationship between the closed loop and open loop frequency response in both plot is split. Okay, why I say split? So we have an open loop transfer function both plot. Am I right? Both plot. Then we have a closed loop transfer function both plot. So we cannot consolidate these two graphs. You mean consolidate? Consolidate mean combine, okay, between open loop and closed loop in one graph. You cannot combine. It have to be split plotting between open loop and closed loop. Am I right?
Yeah.
Okay. So therefore, there is another way that we can see the open loop and closed loop transfer function in one plot. Okay. So we are using a Nichols chart. So Nichols chart is a chart that can show the open loop data and the closed loop data in one piece of graph. Okay, compared to the board plot, which you need two plot. Okay, and then each plot have another two plot, which is the magnitude in decibel and phase in degrees. Am I right? So you have four graph. Open loop dB, open loop degree, then closed loop dB and closed loop degree. Okay, so with Nichols chart, it solves everything where you can see the open loop data and the closed loop data. Okay, you can see here is the magnitude and this is the phase. So outside the chart is considered as the open loop data, open loop magnitude in decibel and open loop phase in degrees. Inside the chart, we have a circle there, one circle, 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 and then another circle, okay? So that is the open loop, closed loop magnitude in decibel and closed loop phase in degrees. So all in one graph, right? So this is the examples. We are using the same transfer functions, which is k s plus 1, s plus 2. So we plot it, okay, using the command Nichols G. Okay, there is a MATLAB command, Nichols G, so you can use this command. If you cannot find it, just type help Nichols. Okay. So from the chart, we can obtain that the magnitude and the phase degree is here, the data. Okay. Then we plot it. Okay, so you can see that there is two graphs. One is k equal to 1, okay, which is this one, and k is equal to 3.16, which is this one, based on the data that we calculate. Okay, usually this data is taken from the open loop both plot transfer functions. So the stability margin is similar, but is gain margin is 15.5 and phase margin is 55 degrees positive and it is stable. But unfortunately, for the exam and test, Nichols chart is not included. Okay, so just take note. Okay, the information of MP, omega P, and omega bandwidth. Okay, just you know that you can see the data of open loop and closed loop in one chart. Okay, using a Nichols chart. Then there is another relationship between the damping ratio and phase margin, which is represented by this formula, which is a phase margin. Okay, it's equal to inverse tangent 2 zeta divided by square root minus 2 zeta square plus square root 1 plus 4 zeta power of 4. And this equation, this curve is represented by these equations, okay? The standard graph. And it's also attached at the test and the exam papers. Right, then we go to the steady state error for frequency response. So as you know already that this is the standard closed loop control system where you have the input R and output C, and E is the error, which is equal to R minus C, and this is the open loop transfer function. The error is represented by this formula, which is a steady state error. Okay, limit S to 0, S or S, R is the input over 1 plus GS. GS is the open loop transfer function. And as we know that we have three type of steady state formula. One is for the unit step input, where steady state is equal to, this is a step 1 over S. Okay, ESS is equal to 1 over 1 plus KP. Okay, so please remember this. And KP is the position error constant. And the steady state for the unit ramp, which is 1 over S squared, is ESS is 1 over KV. Okay, where KV is the velocity error constant. And for the steady state for the parabola, which is 1 over s cubic, so the steady state is ESS is 1 over KE, where KE is the acceleration constant. So this one is usually referred to type 2. This one is type 1. And this one is usually referred to type 0. Okay. So all of the steady state formula can be structured and accumulate as shown in this table, where the steady state error for step is 1 over 1 plus Kp, 1 over Ka, 1 over Kv. Okay. It's shown here based on the type 0, type 1, type 2. Okay, so this one is 1 over S0, 1 over S, 1 over S squared. Okay. So steady state error from the frequency response also the same. Okay, so for a unity feedback system with the open loop transfer function, the steady state error for system type 0, 1 over 1 plus Kp, where Kp is equal to limit S to 0 GS, position error constant. For system type 1, the steady state error is ESS equal to 1 over Kv, where Kv, not Kp. Please rectify your slide. Kv is equal to limit SGS, okay? Then for system type 2, steady state error is 1 over Ka, where Ka is equal to limit S square GS, okay? So steady state error also can be found from the frequency response. For example, system type 0. Okay, so system type 0 can be usually the transfer function have 1 over s plus 0 power of 0, which is 1 lah. Okay, so the steady state error can be obtained from the open loop both plot via Kp. This is the samples, okay, the magnitude curve, okay, in decibel. So let's say you have this plot, the blue line. Okay, how to find Kp from this graph is you look at this point. Okay, let's say this point is 10 decibel. Okay, so 20 log Kp equal to 10. So what is the value of Kp? What is the value of Kp? Safwan. Safwan. Muhammad Muatasim. Tak ada. Nur Izzah Hakimah.
Yes, doctor.
What is the value of Kp if this point is 10 decibels, the initial points?
3.162.
How you get it?
10 to the power of 10 over 20.
So,
3.162.
what?
62.
6. So this
Yes.
is the value of the Kp. Very good. Okay. So what is the value of 20 log 3.62? Nur Izzah Hakimah?
10.
Okay, so here is samples type 0. Okay, why type 0? Because this one. Okay, S power of 0 is 1, so meaning there is no pulse at the origin. So we plot it. So we obtain here is 16.9. So what is the value of Kp? 20 log Kp equal to 16.9 decibel, Kp is equal to 7. Okay. So what is the steady state error? Imran Hakimi. Imran,
Yeah.
what is the steady state error?
Steady state error 1 plus keep
1 divided by 8.
0.125.
Brilliant. Okay. So that is how we calculate Kp and steady state error from sample of system type 0. Okay, now we move to system type 1. Okay, so this is a sample of the plot magnitude in decibel. So for this type 1, so you have to use a ruler. Okay, you find the slope here, minus 20 decibel per decade. Okay, so you use a ruler, go down until it cut the frequency value here. So that frequency value is the velocity error constant, Kv. Okay, Kv. Sample. System type 1. See? System type 1. Nampak? Can you see?
Yes.
Yes, doctor.
So you detect the minus 20 decibel slope, which is here. You use a ruler. Okay. So what is the Kv value over here? Helpful.
Is it 1.15?
1.15.
1.5?
I'm afraid answer is wrong, brother. Eskandar Zulkarnain. Tak datang. Osama Belhaj. Osama. Sleeping. Adrian.
Yes, doctor.
What is the value of Kv?
For KV, 5.
Huh? Sorry?
5.
5.
Based on the graph is 5.
5 radian per second kan?
5 radian per second.
The answer is there. So Kv is equal to 5 and the steady state error will be?
It
Adrian?
will be 1/5, 0.2.
0.2. Okay. Very good. Okay, and then system type 2. Steady state error also can we find from the system type 2 both plot where Ke, you have to find the Ke, but you have to find the slope of minus 40 dB per decade. So if you find the initial slope at minus 40 dB per decade, so you have to use your ruler, go down, and this is the value of Ke, which is square root Ke. Okay, square root Ke. So see the examples here. System type 2. Why? Because S squared. So this is the slope line, minus 40 dB per decade. Then we use the ruler, so the square root Ka is equal, what is the value of Ka? Over there. Sadenan Sakib.
Yes, doctor.
What is the value of Ka?
It's 9.
9. How you get 9?
It's been given there.
Square root Ka is equal to?
3, so
Square root Ka is equal to 3.
so whenever we're
This one. 1, 2, 3. Okay. 8, 2, 10. Correct.
Yes.
3 radian per second, am I right? So Ka will be P square, which is equal to 9. And the steady state error? Right? Sarina sakit? 1/9?
It's 0.11.
0.11. Remember. Okay. So this is another example for system type 0 and type 1, how we calculate the Kp, which is 17.78 and 0.55. Okay, so you can look at it. System type 2, where square root is equal to 3. So this is what from the book, but from the book is very difficult because the plot is not user friendly. So I use my plot and explain to you. More or less is the same. Okay. So we have covered the graphical analysis using a board plot and Nichols chart. So you know that Nichols chart is better because it can give a closed loop data and open loop data in one chart compared to board plot. You have to split. Okay. Stability analysis also can be looking by gain margin and phase margin and some relationship between the open loop and closed loop system information. And I left to you the tutorial for you to review, okay, during the holidays next week. So tomorrow, Wednesday, 12 p.m., no class. Guys?
What? Okay.
Wednesday, 12 p.m., no class. So I'll let you go, okay? Go back to your hometown, okay? Have a rest for 1 week plus during Time Mubarak. Okay, assignment will be sent by e-learning and WhatsApp, inshallah.
Would you like to brief as assignment, Doctor?
Inshallah by next week. Okay, 1 month period.
Doktor, ada quiz kan Doktor? Wednesday?
Quiz is on the Wednesday, 9:30 p.m.
Okay.
9:30 p.m. After Tarawih. You do Tarawih? Tarawih or not?
Tak, Tarawih.
Okay, 9:30. As usual, you have to follow the time. Start 9:30. I think 9:50. Okay. So 10 p.m. Sleep.
Yes, Doctor.
5%. Scope, PID controller, chapter 2. Quiz 3, chapter 3. Quiz 3, not yet. Arab brothers, any questions from Arab brothers?
Doctor, 10 minutes
20 minutes. I say 20.
20. Okay.
Arab brothers, any questions?
Okay, Doctor.
Ala?
No, thank you, Doctor.
Ala?
Yes, Doctor. Can you hear me?
Anta fahimta?
Fahimta, Alhamdulillah.
Fahimta? Alhamdulillah. Shukran.
Thank you so much.
Thank you so much. Any question?
All clear. Everything's cool.
Sira Ahmad, any question?
Okay for now.
Okay.
Yes.
Norina Shafika, any question?
No, Doctor.
Nur Iza Hakima, any question?
No, Doctor.
Okay, if there is no question, so we ended our lecture here. Then I will see you in 2 weeks' time. So next week is the semester break. So you have a holiday, I think 2 weeks time, to give more rest time, okay, for you to celebrate with your family. So stay safe. Please follow SOP. Don't go anywhere unless it is important, okay? So please, look after yourself, inshallah. Subhanallahi wa bihamdihi, subhanallahi wa bihamdika, asyhadu an la ilaha illa anta, astaghfiruka wa atubu ilaik. So thank you very much. I wish everybody selamat Hari Raya, okay, for the Muslim students, okay, and happy holiday, okay.
Thank you, Doctor. Selamat Hari Raya to you too.
Selamat advance Hari Raya to you.
Advance Hari Raya to you, Temple. Thank you very much. Eid Mubarak, Arab brothers.
Eid Mubarak, Doctor. Thank you very much for your effort.
Jazakallahu khairan.
Mubarak, Doctor. Assalamualaikum.
Mubarak.